Não precisa. Deixa-me só dizer ali. Obrigado. Esse adaptador fica aqui, caso alguém tiver um Mac ou coisa assim. Exatamente.
It's not working?
No, I think it is. Just have it connected, yeah.
Do you want to stay here?
No.
Oh, okay. Just 1, 2 or 3 minutes and we start. Okay. I will introduce you. It's okay. I think it's okay. It's better than it yesterday. Okay, hello everyone. Welcome to the second day of this workshop. Welcome to those who are online too. We'll start this day with an introduction to performance and parallel computing, find and release the brakes by Mr. Milan Kloer. And Milan is a climate scientist at the Massachusetts Institute of Technology. He did his PhD at the University of Oxford, working on climate model development, low precision computing, data compression and information theory, predictability of weather and climate, and software engineering. During that time, he proposed the bitwise real information content as a way to distinguish between valuable information and noise in climate data, with the reference implementation bitinformation.jl. He currently develops speedyweather.jl, a global atmospheric model designed to be a computational research playground to develop prototype ideas on computationally efficient climate models. Milan, thank you.
Thank you. Hi, good morning, everyone. This presentation is on the Julia.io GitHub repository, so you can actually basically, while I'm going through this, you can absolutely follow along and basically execute the same lines of code at the same time if you want to. But my idea for the next 45 minutes or so is that basically we will run through this together. And I would love this to be very interactive, so if you have any kind of question or so, feel free to ask them immediately. As just mentioned, I'm probably in the Julia world known for this project called Speedy Weather, which I've probably spent my last year and a half, almost 2 years on, which is an atmospheric model. Basically, it's actually several models in one. I don't really want to talk about speedy weather today, but if you have any questions, obviously feel free to reach out. The only thing I want to show you today is some videos so that you can get a feeling of what it can do and what you can do if you just use it. So this is a simulation of relative vorticity that I painted so that it looks like clouds. It's not actually clouds. And there's another simulation here of temperature. They're all idealized for the moment. There's some nice relative vorticity that gets stochastically stirred, and you look down from the top, from the northern hemisphere. So this is what this model also can do. Or here there's a simulation of waves in the atmosphere. And this is all done in Julia. And obviously, in order to make this work, I had to think about some of these like performance and parallel computing issues. And this is basically why I'm here today and what I want to tell you, some of the like tips and tricks of like how can you do this, how can you, if you think your code is not fast enough or you would like it to be faster, which are the steps you can go through in order to understand what's actually happening. Great, so I'll basically start with the performance part, and then we go on to the, I think, where was it? Zen mode. Look at that. Cool. Start with the performance, and then definitely go into the parallel computing a little bit at the end. And for the performance, I'm definitely going to go through some examples. Going to tell you a little bit about benchmarking. Intermediate representations that Julia uses, but then also definitely very important are like memory allocations and common pitfalls. So let's just start straight away with an example. So let's say you want to compute something like a Gaussian, right? So the formula is there. You may want to naively put this into a function like this one, right? So you have some argument x, you have some mean value mu, you have some standard deviation sigma, and you just put it down there. You put like a little @ in front to make sure that it works for individual scalars as well as like vectors, matrices, and so on and so forth, whatever you evaluate. And now the question is, well, you can just naively write this down, but would you actually get the fastest code if you do it this way? Little hint, most of the time in Julia, yes. If you try to do the same in Python, you probably won't get the fastest code. But how do you know? And this is really the important part, and this is why I call this talk like find and release the brakes, because often we sit there and we're like, I don't know, how is that the fastest it could be? Could it be faster? Right? So we heard yesterday already that Julia is a fast language. So you basically have to imagine you're sitting in a sports car, but you don't actually know whether you're at full speed or whether you actually have the brakes on. And with Julia, most of the time, you sit in the sport car and you go very fast. But in case it's not enough, you want to basically make sure, and this is what I want to convey in the next 45 minutes, is like, how do you find out that you're actually going fast, and how can you figure out if it's not? Simon?
What is the add dot syntax?
The what? The add dot? This one. I'm sorry, this is a little macro that basically puts a dot in front of every arithmetic operation here so that it just broadcasts it across. So you can think of x now as a scalar, but it would also work on a matrix, because like if you want to, so example, the exponent would then need to basically have a dot here if that was a vector or matrix, and the add dot just does it for you and just puts dots everywhere. Just a little thing so that it works on, you can throw in an individual number as well as a vector or matrix or whatever. So let's try this. We just create this function. Let's see whether it does what we want it to. We just create a little vector of some numbers between -3 and 3, evaluate this Gaussian, we get some numbers out, and of course we're using chiromachy. How dare would I use something else? And 3, 2, 1, if it's there in a second, we'll see that there is a beautiful 3, 2, 1 Gaussian. Okay. Anything that takes longer, you have to blame Simon for. Any time that's spent now, we have to blame you for. And wonderful, we have Gaussian. So we know that our function does the right thing, right? But the question is really like, how do we know it's the fastest way it does it, or like the memory efficient way, most memory efficient way? So Julia provides you this little macro that says at time. At time, whatever follows afterwards, it basically just puts a little tick-tock around it, a little clock. So it basically just looks at the clock beforehand, evaluates what's in between, and then evaluates the time afterwards. So the first time you do this, or like if you run this, you see you get a little, like, okay, this took about, here's 15 microseconds. It tells you it had to use some allocation, so it somehow allocated 5 kilobytes of memory somewhere. But really the question that I asked before is like, how do you know that this is actually fast? How do you know that this measurement is robust? Like if I execute it again, it's suddenly 17, 22. How do we know? And then the question is also, how do you know what actually Julia translates this code that I've just written into, right? So does it, I don't know, does it really take all the shortcuts that's possible, or does it take any detours in the way how you've written that code? And this is just an example because, I mean, I've thrown in double precision numbers, so float 64. Let's say a lot of data comes in 32-bit. If we try to do this, maybe it should be faster because you're actually using less memory. But for some reason here, you see, actually it didn't use less memory, and it wasn't also necessarily much faster. So I basically just want to show you some tricks of like how you can do this. And to show you the opposite is basically I wrote the same function, but more in like the old school way of doing it. So maybe some people of you have learned some C or Fortran, where you would always declare everything, and then so I basically went on and said like, okay, well, I know my X is supposed to be some array of like some double precision numbers. Maybe I need to check the size first. I need to allocate whatever output I wanna have. I may want to like pre-compute this scaling constant, and then I would go for I in every element, and then I basically evaluate here my Gaussian, and then return the whole thing. So this function is basically supposed to do exactly the same thing as the one before. And maybe, if you come from the C and Fortran world, you would think like, oh yeah, this is the fast way of doing it, and the other one's the slow one. This is definitely something that would be true for Python. But here, how do we know? Well, measure it, right? And so this is really probably the one take-home message you should definitely have is, if you're unsure, you always have to measure it. Even if you're really smart and you understand a lot about Julia, you still probably want to measure it because you never know exactly what's going on under the hood. And you see here, actually, the old school version is actually not faster. It's just more code, but it isn't actually faster. And then if you try to do the same thing with the Y that I created before, that's the single precision version, suddenly it throws you an error because I was too specific here. And so actually what we just did is like we created a longer piece of code that was less generic, so I can't suddenly use it with something else, and we didn't gain any speed advantage. And so this is kind of like a typical pitfall that where I definitely started with Julia is like, oh yeah, I would like kind of want to write everything down by hand as much as possible, but no, you don't necessarily always end up with faster code. And so, yes, oh my God, my function doesn't work anymore in a general way, so this is not good. Great, so let's understand benchmarking a little bit. The @time macro is quite nice, but you can definitely do better because there's this wonderful package called benchmark tools. Benchmark tools, you just basically say, using benchmark tools, if you haven't installed it yet, you just have to do as we learned yesterday, you just have to add benchmark tools. And so, for example, here, I just like, you can forget about this, is just that I don't want to wait that long. And so the typical, oh, sorry, it didn't execute this one. The typical way of how you would use benchmark tools, this is @btime. So instead of @time, you would just put an @btime in front of it. And now you actually, instead of measuring it once, what it now does is basically measures it several times and actually checks for this in a more statistically robust way. And so now you get actually, oh, takes about 200 nanoseconds. So this measurement is actually also much more accurate than the one before, which basically here said 5 microseconds, which is way, way, way higher. This is because it does this it does it several times and basically checks that. But you see the allocations are the same. If you want to have a bit more information, and this is actually what's happening under the hood, you can use with this @benchmark macro. And this @benchmark macro gives you a lot of information of what's actually happening. So this creating some random numbers here, it actually did it 714 times. So it basically puts the same operation 714 times in a row, measures the time at the beginning, at the end, and then divides it by 714. But in order to get some statistical robustness, it don't just do it once, but it actually does it 7,159 times, and therefore can create some kind of a histogram. And this is what you see down here at the bottom. It's a nice little Unicode plot that shows you actually most of the time it took around like 200 nanoseconds, but sometimes it takes much, 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 much longer. And this is something definitely to be aware of, that because we are allocating memory here, so we've evaluated this one like, I don't know, what's that, 100,000? No, almost 1 million times we've evaluated this one, every time allocating 5 kilobytes. And so you basically just keep piling up memory, and at some point your garbage collector has to basically remove that memory again because it's not used anymore. And so in these cases, you can actually end up with code that more sits up here because it has to do something else. And this is where what this GC means, is garbage collection. And so whenever it's the fastest, it was actually basically didn't have to do any garbage collection. That's something Julia does for you and does under the hood. But sometimes it basically just takes longer. And you can see that actually measuring something isn't actually really, really trivial. It is something that's super complex because things can just, for some reason, just take longer. But so people usually look at the lower end of this distribution. And so if we now compare the Gaussians we have defined before, you can see now you actually do the whole B time. You see it actually takes basically the same time. The old school way of doing it, I actually managed to have less allocations, but it's not actually faster. And it's basically most of the time, and this is the good message, is always like most of the time, if you write it the naive way in Julia, you get actually usually quite fast in terms of speed. Alex?
There's also another way to implement Gaussian, so if you go after.
I'm pretty sure there is. to this version or the other one?
Normal Gaussian.
What am I doing?
When we see
Yeah.
if you want to remove the adult macro,
Yeah.
we call Gaussian with dot. So Gaussian
Yeah.
dot x.
Yeah.
It is actually faster. I don't know why. So
Yeah. So exactly. And so this is where things get really interesting. Now you've understood how benchmarking works. You can basically suddenly start trying to play around with little tweaks and so on. And it told me a lot about how Julia works under the hood by simply just like trying things differently and understanding, is it faster, is it slower? And this is exactly where like benchmarking is. You have to be a little bit like playful and like try out things because most of the time it's impossible to know exactly what happens under the hood. However, impossible to know what happens under the hood, I want to cover this topic a little bit because with Julia, it's the nice thing, you can actually know what's happening under the hood. There's many other languages that's a bit more hidden, but Julia can be actually quite transparent about what's happening under the hood. And so, as a question, you see here 3 implementations of basically the same function, x times e to the power of y. X and y are input arguments, so f1, f2, f3. And the question is, which one is the fastest? What do you think? F1, F2, or F3? Some guesses. Who's for F1? No? Who's for F2? Ooh, do you think like F2 is the fastest? F3? No? No one? Exactly, so like in most cases it's really, really difficult to know. Let's execute them. And I'll show you in a second which one is the fastest and why, and actually 2 of them are exactly the same, although they don't look the same. The way how Julia works is that you write Julia code, right? So you can look at Julia code and you look at it. Once you hit enter, what Julia does is that it lowers this code, as it calls it, like there's several intermediate representations till it's translated the code that you've written into machine code. And Julia does that in several steps. So there's this, what's called typed code, and basically on every single of these steps, it uses several shortcuts. It kind of makes, it kind of infers certain things that you've written. It realizes, oh, this is a constant, so I don't have to recompute this. All of these different steps happen at several different levels in this code compilation. And so, yeah, typed code is the first one. Then you have some kind of what's called the lowered code. Then Julia translates it into LLVM code. LLVM then translates it into assembly code, and assembly code is then actually basically the step before the machine code, what's then actually the machine instructions. And so usually we think of this as like more readable at the top and less readable at the bottom. But actually I still find the LLVM code not too bad. So I would never want to write it, but it's actually okay to read it. And so I just want to give you a little example of the first function in LLVM. And so this is what this code looks like in LLVM. It's obviously not one line of code anymore. It's like several lines of code. But it basically tells you that it has defined a function, f1 here. It will return some kind of double. It has as an input argument a double here, a double there. And then it realized that, well, you want to do some kind of like to the power of function. This function comes from this math constants in this line. You can look it up if you want to. But what it actually then does and what it actually compiled it to, that it just calls this exponent function with the argument that was the second here, that's the y, returns a double, and then actually multiplies 2. That's the first argument here, the %0. And then the %2 was the result that came from here, and then it returns the result that was here. And so you can directly see the individual steps that Julia translated this function to. And now the little surprise is that the second function, remember the first one was written like this, the second one was written like this, so the one has a completely different function here, but it actually, and if you look into the details, it actually compiles it to exactly the same code. This one here is taken from math constant, but actually the call to this exponent function is still exactly the same as before. And so function 1 and 2, even though you've written them differently, are actually compiled to exactly the same function. However, function 3, and I don't want to go into the details, but I realized that it's like whatever happens here, it's a really long piece of code, so you can probably assume that whatever is happening there is not the smartest way of doing it. This is because, and I try to understand why this is happening, is that once you've executed the exponent 1, so this is then suddenly just a floating point number here, and then you have floating point numbers to the power of some floating point numbers, and it basically has to do a lot of if things, because what happens if something is different, and the power function will then basically return something else. Whereas the exponent of y is a much faster way of writing this. So 1 and 2 are equivalent, but 3 is the way more complicated and long version. Great. Let's talk a little bit about allocation, because every time you compute something, you also need some memory. So I'm just like creating an 8 megabyte array here, and the one thing that I wanted to show you is that what happens if you accidentally need to allocate more memory than you would really need to. And so there's two functions here that I've written. The first one just computes the norm. So you take every element in the matrix, you square them, sum them up, and then you take the square root of those. Simon?
Yeah, it's just a small comment, but it's not too before you came. On my version of Julia, function 3 is also identical.
Ha! So I don't know what's happening there, but see, this is always good to realize that actually these are tools that can help you to understand what's happening under the hood. And so I would be curious to later check why it's actually then translated to exactly the same. Exactly, so with this matrix norm here, so what we basically want to do is we just want to calculate the norm of 2 times the matrix. Mathematically, that's equivalent to calculating the norm first and then multiplying it by 2. But under the hood, 2 very, very different things happen. In the first version, taking this matrix A and then multiplying it by 2 basically means you have to copy the entire matrix, multiply every element by 2, then you have this second matrix that's just, every element is just twice as big as before, and then you throw it into the norm function. And on the, this was the first, and on the second one, you just take the matrix as is, you don't have to allocate a new chunk of memory, you just calculate the norm and then you multiply it afterwards by 2, which is the same thing mathematically, but it has very different performance implications. The little dollar sign, you can basically ignore this. This is just a little tweak of benchmarking that makes the benchmarking more accurate. So you can just forget about it. And you see that the first version that I wrote down is actually something like 3 times slower than the other one. And you probably can see here this is because the first one, because we started with an 8 megabyte array, suddenly also had to allocate a second array that was also 8 megabyte in order to compute what we wanted to compute, whereas the second version doesn't have to allocate anything and still gives you, as you can see, exactly the same result. And so these are usually things you have to be careful with, not if you run like super, super small programs, because allocations aren't always bad, but imagine your array wouldn't be like 8 megabyte, but like 8 gigabyte, and suddenly you would need to like allocate this entire array once more. And if you want to do big data, you have to be really, really careful with like what you're allocating. Do you create anywhere like a copy of an array that you wouldn't need to? And also every time, and so maybe this is just to make this clear, in this, wherever you compute this like 2a here, you basically have to copy the entire array, multiply everything by 2, so you have suddenly 2 versions of your same array, one multiplied by 2, the other one not in memory. Then you compute the norm on this one, but then once this function is done, and once you hit the end here, the 2a cannot be used anymore because the function is over. But it's still there in memory, and so this is now where your garbage collector comes in and realizes, oh, you have this array here in memory, but actually no function can use this anymore because it's not returned from the function, is not something that exists outside of the function body. And so it basically says like, well, you don't exist anymore, so I have to erase you, and this is an additional step that needs to be taken. And that can be performance critical, but not always. So especially for big data things, you should always consider or like think about in-place operations. Often they're called with this like exclamation mark because they somehow change the input arguments. Or also views. I'm not really going to talk about views today, but there's basically ways to create, like if you create a transpose of a matrix in Julia, you don't actually copy the matrix. You basically just say like, well, just swap the I and the j index. And so you never actually copy that. And so being aware of these is really good. Basically just to show you one example here, this is from FFTW. This is just the Fourier transform package. I'm just creating a large vector of random numbers. And I've just transformed them to Fourier space, transformed them back, so technically you should get the same thing. And once I do this with allocation, so like basically you throw the array in, and then you get a new array out, meaning you have you have the non-transformed version, you have the transformed version, and then you create also the back-transformed version. And the other one, with the exclamation marks, basically just does that all in place. And so you see that performance-wise, they're actually not that different in this case. It doesn't have to be. Allocations aren't necessarily always bad for speed. But in terms of memory, there's a massive difference between the two. And so if you run into like some big data problems, think about what which memory you're allocating, because often it's not necessary that Julia can remove all of these allocations for use. Great. Then some of the common pitfalls in terms of performance, just to go through them a little bit quickly. One thing, and this is basically going back to the Gaussian definitions in the beginning, these are two functions, they're the same, x times the inverse of x. But once I've added a little, I'm typing the argument here, so I'm basically saying, well, my argument has to be of float 64 to be a bit more specific. And so now we can actually measure, does that make a difference? And so the, am I actually doing this? Yes. So, and the question was like, does that make a difference if I like constrain this? It's obviously really helpful to use multiple dispatch, that you say like, oh, actually, I want this version of the function for a specific type. But here, this would be of the type any, so you could also throw double precision number in. So you basically have the same function twice. But you can actually check this again now with code LLVM that you created, and now you can see here, we have actually created exactly the same function. So the take-home message from this whole typing is like, you should use it in order to make use of multiple dispatch, but it's absolutely irrelevant for performance. Because Julia will basically, at the time where you call this function with a given type, it will compile it to the same function anyway. And so you can add those if it's nice to structure your code, but you don't have to for performance reasons. And this is an important lesson that took me probably ages to learn, that, oh, actually, I thought then if I tell the function which type it should be, then the compiler can take some shortcuts. No, it's not the case. The next point, and I think we talked a little bit about this yesterday, is that often we end up defining our own compound types. So basically just said like, I want to have a point here. A point consists of two numbers, some x and some y. And I have two versions now. So they're both of the type point example, but one is a point number, meaning I've just said like, I want my fields in here to be numbers. And the other one I said, I want my fields to be 64-bit integers. So this one is a version where number could be anything. It could be a complex number, it could be like a kilobyte large, it could be a 16-bit number. So you basically here, you do not constrain at all which size this thing is going to have. Whereas here in the second version, you say like, this point definitely requires exactly 128-bit because it's 64-bit for the first number and 64-bit for the second. And now let's define something like the length of this point, or like the length, you think of it as a vector or whatever. And I'm just defining this function that is, because it is for the type of point example, it is exactly, it would apply to both of those. So I can create two of these points. They basically look the same now because I've both said like x is 1 and y is 2. But still remember that one is of the type point number and the other one is of the type point integer. So the compiler for the second one will always know this is exactly 128-bit big, whereas for the first one, it basically doesn't know, and it cannot infer this just from the type because it's not something known. Like Julia makes all decisions based on the type. And so for this one, it doesn't know what this could be because it could be any number. And this has a massive hit in terms of performance, and I'm just showing this here, where the first one is about 4 times slower than the second. And the reason this is really that for the second, it knows exactly what, how much memory it has to allocate, how big are things that it needs to put into different caches and so on. And it knows this exactly, and so in the first one, you therefore get like a 4 times performance penalty because basically when you execute this function, it doesn't know on the, if it, for example, if it computes the square, adds the other square and so on, it doesn't know, it has to basically still check for the type, oh, am I actually having a complex number that's really large, or am I having a 64-bit number? So it can't do this. And so take-home message from this is every time you create these compound types, a struct, put something concrete in here. So something that is really where the compiler knows how big it is. That's very important. Great. Then, second part. Let's go to... Yes.
To the point number, because especially sometimes when you're running model output, sometimes you're running a field 64, and sometimes you want to run field 32, and quite often in those cases we use structs.
Yeah.
And we
Basically, the rule of thumb is here, you have to make sure that whatever new type you create, that all information is in the type itself. So meaning that if you wanted, you said like single precision, double precision, so meaning if you wanted this to work for both, you can, for example, do this. Then you have the type here flexible, it's whatever type T you want, but it also exists up here in the curly brackets. That is like, it's called a parametric type in Julia. It basically just knows it's a point number of a given type, and both of the fields are of that type. So at the point you create this, wait, let's do this, point float. I should be able to create this. And so I can then, let's go here, point float. I probably can even do this. No. Yeah, sorry, because I didn't specify T, but like let's do it this way, then with 2 floating point numbers. So now at this point, if the Julia compiler makes any decisions on the type of the input arguments to compile a function, it knows the point float, and it knows that it's of type float 64. And you could then basically that way, the Julia compiler can always make decisions on that. And so if you now call the length this function with this type, it will basically compile it for the 64-bit version. Once you do this would be the 32-bit version. Once you call this function, it will compile it again for the other one. And I think we can probably even check that. So let's call this P3. And then length B time length of B3. And then we could probably just check. So you see this is basically the same speed as before, like the fast version. And you can probably check that it actually does that by simply saying length of P3. Oh yeah, it does a bunch of things, but it basically, you see here, it doesn't write double, it writes float. So it has compiled it for the 32-bit float, right? And so it basically creates a different compiled version depending on the type, and because the type is known up here, it can actually infer this. Great. Okay, let's talk a little about parallel computing. I don't even know what time it is. Great, we have another 15 minutes or so for a little bit about parallel computing. There is many different ways of parallel computing, because in the end, we're now on a system where we have several different processors. We have some kind of memory. The memory might be shared between these processors. It might be, we might have it split into different pieces, right? So we can basically think of a parallel computer as like, I have all the people here in the room, right? You all have brains. These are the processors. You all have a laptop in front of you. This is your memory. So now I'm standing in front of you and I'm talking to you. And if I want you to solve some kind of complex problem, there's many different ways of how I could distribute different tasks to different people. You can do your own thing, or you can talk to your neighbors, or you talk back to me. Maybe I tell you, hey, tell the person next to you to tell them something, and I don't actually have to interfere anything. Somehow the whole message runs around. Everyone adds like, I don't know, a 1, and it comes back to me, and I haven't interfered at all. But maybe I create a program that says like, tell me a number, can you add 1 to it, and then I'm communicating back and forth. So there's many ways of how you can make this parallel computing work. You could all sit in front of the same computer, and this is basically what's multi-threading. And so I've asked Midjourney here yesterday what it looks like if 4 people try to sit on the front of the same computer, because this is basically what multi-threading is. Multi-threading is a way of doing parallel computing where you basically have several brains. These are your processors. And you only have one memory. That's your laptop in front of you. And so if 4 people try to write 4 different emails, that's going to be maybe a bit complicated because you all have to access the same memory somehow at the same time, and you kind of interfere with whatever you're writing, like, hello, dear sir, madam, whatever. And it's kind of like, it's tricky because you always have to wait for the other person to be like done with their word before you can write your word. So another way of doing parallel computing would be that you all sit in front of different computers and you write your own emails. But multi-threading is probably the easiest way of doing parallel computing, where you have several brains, but you have the same memory. And this leads to a couple of things that you have to be aware of, and we'll go through these examples now. In order to do multi-threading, what you need to do is this is not something you can do in an existing session, so your results, if you go through this notebook now, might look a little bit different. But in general, you would start Julia with like minus threads 4 or minus T4, or any number you think is reasonable here. It doesn't have to be the number of processes on your laptop or computer or whatever. In this case, I actually have, because I know I have 4 processes on here, but you could also choose something that's bigger than that. So a thread is, you can think about a thread as like a small set of instructions that kind of is computed, and you can basically throw them around. And if basically saying you have 4 threads basically means you can execute 4 sets of instructions at the same time. So I have already, and this is what you see here in the top one, in this Jupyter notebook, I've already started this with 4 threads. And so if I do threads.end threads, it basically tells me, yeah, I have 4 threads. And so I can now basically use the 4 processors that I have on my laptop in parallel. The very easiest probably example is that, and this I'm running through this, what this means here. I'm creating in my single memory, right? So we have 4 people sitting in front of the same laptop. I'm just creating a vector of zeros. And now I run through this loop. This loop has a length of 10. And I basically I split this operation that's coming in the loop. I just split this across all of those threads. So every thread is just supposed to take its ID. So that's going to be 1, 2, or 3. And just going to write this into the place of this vector. So what's basically happening now is that the 4 people sit in front of the computer. The first one says like, oh, I'm 1, and you put the 1 into the array. The second person, oh, I'm 2, you press the 2, and the third person says, oh, I'm 3, press the 3. But the way how threads works is you don't necessarily have this in order. So what you see here, what actually happened, is that somehow the first 3 iterations of this loop were claimed by the first thread. Then the next 3 were claimed by the third thread that somehow was faster than the second. The second was somehow at the end, and then the 4th one here. It can be that if I execute this again, something else happens. You see, now it's basically in order. So now it's 1, 1, 1, 2, 2, 2, 3, 3, 4, 4. But basically in this you have to be aware of, and this can cause absolute problems because you're basically trying to access the same memory more or less at the same time. Here it's at least like one thread only accesses one element of this array. But in which order this happens, you don't necessarily know, because you have 4 people sitting in front of the same laptop, and they're kind of fighting to press the button at the same time. And this can cause problems, but this is kind of how multi-threading works. 4 people sitting in front of the same computer. And to reveal which problems this have, I just wrote this little function called race, because we're going to talk about race conditions. And race basically just says like, I have a variable that's called A, and it's 0. And I tell all of the people in front of my computer, the threads, I tell them to add 1 to this A. And then at the very end, you just return the value of A. So if I execute race with 100,000, I basically tell 4 people, because I still have 4 threads, to add somehow distributed among them 100,000 times 1 to A. So technically, if you were to execute this 1 by 1, you should end up with 100,000. So now you can guess what's going to happen. It's probably not what you expected, because A isn't 100,000 now, but it's only 25,000. And you're like, what? How does that even work? And the problem here is what is often called a race condition, because several people try to access the same memory at the same time, or you basically try to write this like 4 different emails at the same time. Obviously, there's going to be garbage coming out of it. And in order to understand this a little bit better, I've taken this little picture from Wikipedia, where, say, thread 1 and thread 2 both have the task to take a number from memory, increase it by 1, and then write it back. You can have it that thread 1 has finished the reading it in, adding 1 and writing it back before thread 2 does something, but you can also end up in this situation, so that thread 1 reads it and says like, oh, A0. Then thread 2 reads it, oh, A0. And then they individually say like, oh, I add 1 to it. Amazing, we have 1 now. And then you write them back. And so in the end, you actually end up with 1 instead of 2, which you would have if you would have executed the thread 1 first and then the thread 2. So these are the kind of the headaches you have around parallel computing. And here, what happens is that because in this little race function, because we have 4 threads now, somehow, somehow like basically only like every 4th time 1 is actually added, and I believe this is because the 4 threads try to access A, read A, have 0, they all add 1, and you basically have only, you end up with 1 instead of 4, because they basically have, you can think about this as like, you have like 4 columns now. But sometimes one of the threads is a bit slower, and so you actually end up with a number that's a little bit higher. And this can absolutely be like really weird things can happen here. So if I execute it with 1,000, then actually I end up with like about 50% of the number that I should have, right? If I do this with 10, oh, forgot the parentheses, then I actually end up with 10. So there are very weird things that can happen. They are unpredictable, and you should absolutely always try to avoid this because it can lead to mistakes. It's very difficult to debug what's happening here. And so instead of showing you examples that don't work, I wanted to show you one example that absolutely fine works. And so basically this is the take-home message from you, is that multi-threading works really well and it's also easy to implement if you think about do not access the same memory at the same time, because then you won't have this. In this example, I'm just created a random matrix of 10 by 10 with some numbers in it that's now in my memory. And then I tell the 4 different threads to take a column of this matrix and sort it. So every thread is just gonna illustrate this. Yep. So every thread took 1 column here and sorted this just from the smallest to the largest number. And the next thread took this. I don't know whether thread 1 took this one and thread 2 took this one, then thread 3, or whether it was in another order. But it also doesn't matter, because you basically end up, with the same result. Because, and this is the important thing here, in this case, I have deliberately avoided situations where one thread accesses memory that another one was still accessing. And so, because the columns are independent, there's no communication or like accidental miscommunication between those threads, and you can, so multi-threading is a very good way to do something where your whatever memory access is completely independent. So let's say you want to, I don't know, you have 30 years of data and you want to, you take then 4 threads and you say for every year of data, take that year of data, load it in, compute a mean or whatever, and write this mean to a file. It's absolutely fine because you do not have any interdependency of the data. And this is kind of the way to do it. The second way of parallel computing that I just want to touch on, because it's also really nicely implemented into Julia, is distributed parallelism. So now we don't have 4 people sitting in front of the same computer, but now we have 4 people sitting on front of each of one computer. So we have 4 people and each one laptop. And so they now have independent memory. And so we have to be a bit more careful about like what actually we communicate. However, good news, Julia makes that really easy for us, because basically Julia takes care of all this like communication. So, and I go through this in a couple of examples. To go back to weather and climate, I thought I'd show this little figure, which is, I don't know, maybe one of the first ideas of like distributed computing. This is an illustration of some, whatever, probably 80, 90 years ago or so, where Louis Fry Richardson was basically imagining of how you compute a weather forecast for the world. It's an artist's impression of that. But the idea was that instead of having one person that computes everything, you basically split this problem, because he realized that it was a really, really big computational problem. You could split this problem into having one team of computers. Back then, whenever he talked about computers was actually human computers. That's why you see these people sitting around the inside of the sphere here. And so you had like one team computing things for North America, one team that computed things for South America, and you see that there's this like group of teams somehow standing in the middle of this sphere. And so the idea was basically that whoever was computing something for, let's say, I don't know, Brazil, that Brazil was then communicating to Uruguay and Paraguay, so they have communication to the left and to the right, but they would still have their own memory in front of them because they could do their computations in front of them, and then they would also report, they could then also report back to this central main, and this is where I think then the communication is supposed to happen with this light, and you basically say, you tell me your number, you tell me your number. I mean, this obviously never happened, but the idea behind it is still very, very similar. So now you basically have a situation where everyone has their own memory, their own communication, and you have to communicate. In a weather forecast, you would need to communicate to your neighbors and maybe also to the central thing in the middle, because maybe that's the one that actually then writes down the numbers for like, and then basically records what's happening. Okay. So how do we do distributed computing? In Julia, that happens with this package called distributed. So you say using distributed, and this is actually something you can do even though your session is already running. We're now adding add procs. Basically means I'm adding 4 workers, as they're often called in Julia. So workers 2, 3, 4, and 5. They get as an idea because now we're basically in the situation that you've numbered different teams here, 2, 3, 4, 5, inside the sphere, but 1 is actually the thing in the middle. So you kind of can think of this as like, let's say I'm the 1, and I'm telling you different things you need to do. And I just want to give you a little example of how you could do this. So this is just a little snippet of code where the task that I wanted to have is like, can you do a prime factorization of the number 1 million, but also of the number 1,000,001, 1,000,001, 3, and so on, until 10. But I don't want to do this all after another. I want to share this task and distribute it across. So it's basically, imagine that I'm the person running through this code, and the first thing that I do is I tell different people of you, say like, can you use primes, the package primes, and I basically tell all of you, you all load your package prime. Then I'm saying, okay, I want to distribute this, and I'm sending now the number 1 million to you, and ask you to do the basically what's inside. And I send the number 1,000,001, I send it to you, and I ask you to do whatever is inside. So whatever you do, you have your computer in front of you, you can execute it. Whatever you do, you have to execute this. Maybe you want to report this back, but in this kind, it's actually just like printed here. And so if I execute this, we'll see this in a second what happens. You get something like this back. So I've somehow sent the number 1 million to worker 2. Worker 2 says 1 million prime factorization of that is 2 to the power of 6 times 5 to the power of 6. Wonderful. Worker 4 said something different. Then actually worker 4 also returned the 1,000,006, 1,000,007. You see that this order is completely whatever, in whichever way these processes were done. Obviously, the prime factorizations may differ in terms of complexity, how difficult it is to compute this, but basically the way how they return it could be absolutely seemingly random, because it just happens depending on whatever happens on your computer. And so this is a way you can use distributed computing in order to like split up a task. This may not be always super exciting, because often you want to have this like central entity in the middle that gathers something back. And so I've created this little example that basically says like, I want to flip 1,000 coins. So for I in 1 to 1,000, I'm flipping 1,000 coins, and I want to distribute this. And this is often called the map-reduce framework, because you also define here a reduction function. So what this does now is that I'm basically saying I have 4 workers here. I'm basically saying, can you flip a coin? True, like heads or tail? Tail, right? So I have basically said like, please flip a coin. I've given that task to that person. He's told me tail. I have the tail now. Now I'm saying heads or tail? Heads, right? So I have basically, I received a 1 and I've received a 0, and I'm actually the one adding the 2 then together, because this is exactly what's happening in this reduction function. And then in the end, I'm the person who then says, okay, n heads is actually the numbers of heads or tails or whatever you've counted. And so I basically asked 4 people of you to in total flip a coin 1,000 times, and I've received about 50% of tails or heads back. And so this is a nice way of, for example, let's say, and I think I have another example here. Let's say you have a data set of like, I don't know, 100 years of data. And then you say distributed, but I want to actually reduce them with max because I'm kind of looking for like the maximum value of something for all years and years. So you have like 1,000 tasks. You can distribute them across your 4 workers. And every worker is then supposed to look into, I mean, you may load some data here, but let's say it's just like some random here. You have 365 of days of some random daily wind speed. And then every worker is supposed to calculate the maximum, right? So you would calculate the maximum for the year 1940. And then in the end, you tell me, oh, my maximum wind speed was 3 meters. And I'm basically like, okay, I get the 3 meters here, I get a 5 meters here, or 5. Who has a higher, like, has someone measured 6? Has someone measured 7? And so in the end, you can see here that basically at the prime node, me here, I've actually then received 4 meters per second as the strongest wind in this example. And so this MapReduce framework is another framework that's quite nice, which kind of where it shows you that there is some communication happening, but Julia actually takes care of that communication. So you never have to specify here explicitly who you are talking to with what, right? So you can think of this as more complicated, like to worker 1 send this, let them do that, then receive another message back. But you don't have to do this explicitly, and this is quite nice with this @distributed macro. And then, yes. And then the very last thing that I just wanted to show, there's another way of doing parallelism, especially when it comes to simulations. What often done is called domain decomposition, where you have a certain, for example, you have a certain domain where you want to calculate something, and you say like, well, actually, whatever you calculate at a given point only depends on the point to the left and to the right. And so you could think about process 0 basically covering the left part of the domain and calculating everything that's necessary there, and process 1 covering the right part of the domain. However, things always depend on the point on the left and on the right, so you need some communication at the edge. And so in this example, you can check it out. I have a GitHub repository on where I use MPI, that's another parallelism framework, where actually several workers execute the same code at the same time, but depending on their ID, you can let them do different things. And so here, basically, the left part calculated this part, the right part calculated this part, but you see there's some information propagating through. And this is because I then have to manually, I had to implement, okay, process 1 send a message to process 0. Process 0 receives that, and you then have these overlapping, they're often called ghost points, where you just basically copy the data across. And so process 0 knows everything they have to know to compute whatever's happening inside the domain, but you have this little overlap. And this is very common style of parallel computing for simulations. And this is, I think, where I would like to stop. I'm still around for the entire week. So to summarize, for performance, benchmark it, because otherwise you don't know what's happening. And for parallel computing, actually, Julia makes it really easy. Play around with this. I've shown you 2 ways of doing parallelism. There's a few more ways of doing this. Has an amazing documentation if you want to go more into this, or just ask me a question. Thank you.
Questions? Quick.
Any quick questions? Yes, Alex.
PC cluster where you have special hardware for the interconnect. Can you also use efficiently the distributed package of Julia, or would you need a switch to MPI?
I believe, you may, I think, was it many years ago, where there was this announcement of Julia joining the petaflop club because they managed to run an application on I don't know, some supercomputer reaching overall 1 petaflop of performance. And I believe they use distributed for that, but I'm not quite sure. Okay. But so Oceananigans, for example, uses MPI. They use then the GPU version of MPI so that you can basically split the globe or the ocean into like different chunks, and every GPU takes a different chunk, computes that, and just always communicates across the boundary. Then once you go to 2D, your halo, so like these ghost points are suddenly like basically like a little rectangle around your domain. If you go to 3D, you have to like communicate on all sides of your sphere. That makes up with these things really complicated to implement, but it's still possible to do this with MPI.
And is there a way to check which kind of hardware is used to make the exchange? So if the InfiniBand hardware is used to exchange it, or
I don't know that. Yeah, that's probably. But this is where things get really, really complicated, and I thought I'd leave it on the light side for today. Wonderful.
Okay, thank you. So, time for coffee break. Since we are some minutes late, let's do this coffee break until 10 past 10. For those who are online, we'll be back at 10 past 10, okay? Thank you.